Alright, welcome back, Digital Electronics. Just wrapping up the NAND gate. We are going to step into the NOR gate now. Very similar to the NAND gate as far as all the same kind of procedures that we're going to follow. Only it means not or instead of not and. So basically, same steps, same procedure, being able to redraw circuits in terms of NORs instead of AOI logic. Same concept there. And also, just like we learned with NAND, alright, you can make a whole bunch of different types of gate using a NOR. And we'll do that replacement, making it more cost effective to use NOR logic, just like we use NAND logic to create circuits. Alright, so this is the NOR gate. Notice it looks just like an OR gate, only we put the inverter bubble on the front of it, just like we did with NAND. So when we do that, you do the OR piece. So this is X or Y, and then you invert it, so you draw the bar over the X or Y. Then you can use De Morgan's to break the line and change the sign, so it ends up being not X and not Y. Below you can see the table. Alright, if we substitute in the values 0, 0, 0, 1, 1, 0, and 1, 1, we will get back 1, 0, 0, 0. So remember how in OR gate the the truth table went 0, 1, 1, 1 for the outputs. Notice a NOR is the exact opposite. It's whenever we don't have a 1. In that case only happens at 0, 0. So when we don't have a 1, so 0 or 0, is when we get a 1 for our output. Any other time we have a 1, we will have a 0 for an output. So exact opposite of the OR. Okay, just like we did with NAND gates, we can completely redraw AOI logic for this. So if we want to use a NOR gate as an inverter, we will send one input into a NOR gate, into both inputs. This is a 2-input NOR gate. X will go into 2 places. So X or X is X, and then we put a bar over it, so it becomes not X. So that is identical to how we use a NAND as an inverter gate, sending the same signal into itself. So nothing really new on that one, except for we're using the NOR gate. Now, the NORs and the NANDs are flipped about how we go from NOR and how it relates to a NAND, or I'm sorry, how NOR relates to OR and AND. It's the opposite, but yet similar way when we do that. So if we take a look at this one, and we have 2 NOR gates. The first NOR gate has input X and Y. So when we put that through, we'll have X or Y not. And then we put X or Y not into the inverter again, because it's the same signal going into both inputs of the NOR gate. When we do that, we get X or Y not or X or Y not, which is X or Y not. And then when we hit the bubble, we put a bar over it. So our output is X or Y not, right? Or double bar. And remember, double bar cancels each other out, so we should get X or Y. So this is how we translate X or Y through NOR gates, alright, in the equivalent of an OR. So you can see the truth table down below, same truth table as an OR gate. Okay, so we use these 2 gates, and we're going to do the circuit replacement like we did with NAND. Okay, but we use these 2 gates as NORs, and we can write them as an OR gate. Lastly, we're going to use NORs to write them as an AND gate. So the setup is what you see here. We are going to invert the X and the Y signal using a NOR. We're going to take the outputs of those signals and send them into the next NOR. Those signals translate to what we have on the right. So we're going to have X bar or Y bar, and then a bar goes across it, okay, through that last NOR gate, because the bubble does the inversion. So when we do that, we get Z equals X bar or Y bar, all barred. Then when we apply De Morgan's theorem, we break the line and change the sign. So we're going to have X double bar and Y double bar. So we should get X and Y. So this is how we make a NOR gate turn into an AND gate equivalency. And once again, you know, it's just like with NAND. Since we can make an AND gate, an OR gate, and an inverter all out of NORs, it becomes much more cost effective for us to do that. Okay, we don't have to make as many chips because we can get things done with one chip. So in translation, you need to make sure that these are in your notes. Okay, what an AND gate looks like in terms of NORs, what an OR gate looks like in terms of NORs, and what an inverter looks like in terms of NORs. So we will do circuit replacement here in a little bit. When you get done with your date of birth, I will make you do a chunk of your date of birth, all in NAND or all in NOR. That way you can kind of see how we're going to reduce, you know, the cost of what it would cost for you to create that circuit. Alright, so the process of implementing the NOR, okay, you're going to start with your basic AOI or AND or an inverter circuit. Then we have to identify how to replace them with what we just learned on the previous slide. We're going to redraw the circuit in terms of NORs. And then if you remember, we do the same step 4 here that we did with NAND. We identify and eliminate all the double inversions, and then we redraw the final circuit. Some of you guys are going to try to skip step 3. I wouldn't do that. It'll really help you see the inversions, and I'd like to go over it with you when you're doing that in class, so I can double check and be like, yes, that's an inversion. No, it's not, because sometimes it becomes kind of confusing if it's an inversion or not. But we'll see on the next couple slides here what I mean, and if you can remember it from the NAND, you'll kind of see how, you know, sometimes it was a little hard to tell, but we'll get through that. Alright, so we're going to take the same circuit here. Alright, we did this with the NAND. We have 2 AND gates that we have to replace, we have an inverter that we have to replace, and we have an OR gate that we are going to replace here. So we're going to redraw this same circuit using all NOR technology instead of AOI. Because right now, what do we have to buy? We have to buy 3 different chips: an inverter, an AND, and an OR chip. And we're going to be able to do this hopefully, you know, with just one chip of a NOR. So just like we did with NAND, we take each element one at a time and replace it with its NOR equivalent. So we can replace the inverter, we can replace the 2 AND gates, and we can replace the OR. Okay, everything with its own equivalent. So when we do that, your circuit is going to look like this. Okay, so similarly to the NAND, this one we may or may not have some double inversions. We're going to have to take a look and analyze it a little bit closer so that you can see. Remember, a double inversion is where we have, you know, something going into one of the NORs, and then it goes into another NOR. So eventually we're getting back out the same signal that we sent in. So it's kind of redundant, so we call it a double inversion. So this is the redrawn circuit. Here is a scenario where we have our double inversions, right? So with that, we are able to eliminate both of these gates from the circuit design. And essentially, this is the redraw. Okay, all I did is kind of, nothing else happened. We erased both of those, and I know it looks funky on the next slide. It was more or less to kind of get it to fit a little correctly so that you can see, all right, how the redraw takes place. So we only had one set of inversions that we eliminated, and now we're able to send the rest of these in as such. Now, this one is still cost effective. Alright, because remember, if we go back, there's 3 chips that we had to buy: an AND, an OR, and an inverter. Alright, so remember that there's 4 gates on every chip except for the inverter. The inverter has 6. So if we count up, how many gates do we need here? 1, 2, 3, 4, 5, 6, 7. We need 7 gates. If I can have 4 on one chip, this circuit takes 2 chips. Okay? 2 chips to make this circuit. So it's 1 less than the original drawing. So maybe not as, it's still saving us money, still cost effective, but not nearly as cost effective as the NAND is compared to the NOR. okay? And like I said before, this is something I want you to make sure that you're working on, is that you are drawing all of these and you are writing the outputs of the gates in every single scenario. It will really help you through this. And those of you guys that are, just learning from home instead, I need you to make sure, if the multi-sim online live isn't working right, you're going to have to draw your circuits out by hand. Okay, so just so you know, you are still expected to do all of those. You're going to have to draw them out by hand. It's okay, it's good practice, and it's not as hard as you think. Alright? So, moving on, if we take a look at the total number of chips, which we just talked about, original circuit versus the NOR circuit, we save, at least on a chip. Now remember, if a chip's 30 cents, okay, 30 cents may not seem a lot, but when we're doing, thousands of these, it adds up quickly and starts to save your company lots and lots of money. So that's why it's imperative that we understand how to do NAND and NOR versus just doing regular and or inverter logic or AOI logic when we do our calculations. So hopefully you understand why we're doing NAND and NOR technology. It looks like it's more, but it's really not. It may be more gates, but it's less chips, if that makes sense. Okay, which makes it more cost effective for us. Alright, well, just like usual, if you need a Zoom meeting or team meeting, let me know. Else, email me any questions or ask questions in class. I'll probably go through this one on the board one more time in class, just so that you guys can have the effect and hone us in on it one more time so that you really kind of get it down. Okay? Alright guys, have a great day.